All right. Thank you for coming to this session on extending the ArcGIS API for JavaScript's 3D engine. This is going to be a longer a demo session. It's about an hour. And I'm going to go pretty deep technically into WebGL rendering, things like that, using three.js. So I am expecting that you know already something about like either OpenGL, WebGL rendering. So I'm not going to go too easy. But afterwards you can always ask me questions, obviously. So yeah. So I want to start by talking a little bit about explaining when to extend the 3D engine. And then I'm going to talk a bit about the basic concepts and API behind extending the 3D engine. I want to talk about integration with three.js. And I'm going to talk a bit about advanced data visualization. I'll show, it's mostly going to be demos. I'm going to dive a bit into the code, show you how this is done. Hey, can you actually hear me? Okay, yeah? Okay. So when to extend the 3D engine. This interface that we provide, I put it at the bottom, it's experimental. What we mean by that is that there is a bit kind of a lower level of support for this interface. It doesn't mean that we don't want to maintain it and support it, but it does mean that we might break it in certain ways, more than we would do with the normal API. This is because we want to be able to control like internally how we render, set up the state and everything like that, like the WebGL state. So yeah, but we'll try to keep it very stable, but there's no like strong guarantees on that, so be a bit careful with this. So when to use that? We build it specifically for the cases where maybe you have data that you cannot really visualize, but the symbology that we provide or the type of renderers that we have, or maybe you want to do a visualization or an animation kind of thing that's just not available yet, where we didn't really implement this. You must be familiar with WebGL. We are not holding your hand. We do provide samples. But you have to be proficient in WebGL if you want to use this interface. And you have to be able to afford the development effort because you're pretty much on your own. Like you have to really implement all the rendering yourself. So it's important to know. I'm just going to show you a couple of examples. Some of these are from the APL, the Advanced Prototype Labs here at Esri, of when and what kind of visualizations you can do. So this is, for example, and these ones you can find on GitHub. I put the links here. You can find them. These are from Richie Carmichael. So this is, for example, magnetic field rendering of the magnetic field of the Earth. Another example is he also made this kind of earthquake visualization where you scroll through time and you can see like epicenters of earthquakes and how they expand out. Another example which is interesting is that before we had the point like type in scene layer where you can actually have a lot of points rendered on the globe. Before we had that, the only way to really render a lot of data like this one is by using external rendering. So here he used satellite data. So these are all satellites that are around the Earth, and you can see like he rendered let's say the path of the orbit of the satellites and things like that. So it's also a way to really prototype things out for us before we actually support it fully as part of the API. Some other examples, this is a sample that you can find online in the SDK where we use three.js. In this case, it queries the live position of the ISS, the International Space Station, and then renders it using three.js with a relatively accurate model. And it follows, let's say, the exact trajectory of the ISS, and you also see like from which position on the Earth you can actually see it. And another example that we have, so the thing that we don't do yet is animations or data-driven animations. And this is also a way for us to prototype that. This is a sample that's also online. You can see it. Here there is a feature service behind which provides wind speed data for these, and then we basically render windmills at the exact locations where they normally are, and then animate the blades based on the data that we get from the feature service. So these are the kind of things where you can actually enhance or like enrich your application using this kind of rendering that we don't really support yet fully in the API. The last example, and I will go into details this, you might have seen this also in the plenary, it was briefly shown, I made this specifically for this session. It's a demo using external rendering to render this kind of wind data on the globe. So these are, in this demo, there's 1 million particles flowing around the globe being simulated in real time using pure WebGL. This will also be made available online, and you can look at it. I will go into the code a bit to see how this is done. So I want to just quickly talk about the basic concepts and API that we expose. Obviously, if you compare this to like adding your own graphics in 2D, this is quite a bit more involved. There's things where you have to think about. So you'll have the WebGL context and the WebGL state that you'll have to manage. You have to know about the render coordinate system that we use. You have to know how to integrate the camera, the lighting to get like correct rendering. And the last one, you have to also know some details about dealing with precision issues, stuff like that. I will go into these topics. You can also find them in the SDK. So the main interface and the main API that we expose is in this module, Esri views 3D external renderers. I'm going to briefly go to that page and show you a little bit what that API looks like. So the API surface, like the interface, is pretty small. We don't expose a lot, but we do expose like the fundamentals to get you going and rendering on top of our own render engine. The most important things to know, these are these methods. So the idea is that you can have an external renderer that's a small interface that you can implement, and you can add this into the engine, and then we'll start calling your render method each time we render a frame. So you can have a look at so that's the add method here, where you can add, you say, okay, on this view, add this renderer. The external renderer interface is also very small. It just has 2 methods. One is setup. You can do any kind of like preparing your resources, stuff like that. You get the WebGL context, and then you can just like put things on the GPU, stuff like that. And then there's a render function that gets called each time that we need you to render your own like rendering. So that is called basically each time that we render a frame. You get that. These methods get a context object that contains all the state that you need to know about when you do rendering. So we'll give you the GL context that we use. We'll give you a camera definition, sunlight definition, so we have only directional single source sunlight. You'll get the direction plus the ambient and diffuse lighting parameters. And then there's 2 methods that are important. Reset WebGL state will reset the whole state to a known state that we need to that we use when you come back into our rendering. This is something that you will always need to call at the end of your render step. And then there is bind render target. So we switched to, for example, recently to off-screen rendering, and it's important that you bind back the actual render target that we need at the end of your function, or in between if you switched like to another render buffer, you have to switch back to the one that we expect. This is also important in integration with ThreeJS, which I will show also. I mean, you will see a bit of these definitions. It's pretty straightforward. In the camera, there's a view matrix, projection matrix, so the things that you are expected to see. We have near far plane, the FOV, everything to set up the rendering so you can render in the same coordinate system as we do. I want to briefly have a look at 2 other methods. So the other thing that you need to know is how to go from a map coordinate, so in any kind of coordinate system spatial reference, to the render coordinate system that we use internally. We use, for the globe, we use Earth-centric render system, so the origin 0, 0, 0 is at the center of the Earth. And then basically it's just X, Y, Z. And then I have a little graphic here. These are the axes that we use internally. There is a method, here, to render coordinates, which takes a map coordinate, so in the spatial reference of the view, and will give you the render coordinates that you can then use to render your stuff. And these are low-level interfaces, so you get you can pass in buffers and do many transformations at the same time, stuff like that. I will show you some examples of the use of this. The other important one is render coordinate transform add, which will give you the actual transformation, like 4x4 matrix, to do the affine transformation of any 3D vector into the render coordinate system. This is a bit the interface. You can go through this page. There's a bunch more information on it. I will not go through everything, but some of it you will see during the presentation. So we highlight most of the things that you will need to know about, so go through this if you're interested. So let's start with some small examples. So I'm waiting. Let me try this. I'm sorry about that, I don't know why. All right. So basically what I want to show first is the render coordinate system, like how does our coordinate system work. And I made a small external renderer that's going to visualize the transformation that we have using this render coordinate transform at. So here I have basically, whenever I move the mouse, I'm going to position that coordinate transform, and you can see here the X, Y, Z axis that we use on the globe. So this is basically telling you, okay, the y-axis is always pointing north, right? And the x-axis is always pointing kind of east. And then we have the z-axis, which is pointing always from the surface up. Like that, right? So I can, in this example, I made it so I can actually pin it in screen. So I can put it, I can put it here. And you can see how it rotates with the view. So this gives you a good indication of what that coordinate system is that we use. So if we look briefly at the code for this, I'm going to spend a little bit of time just to explain like how the structure of this is. This is going to be some basics, and then in the other parts to focus more on the differences there. So first, let's have a look at just initialization. So this is my custom renderer, implements this interface, has setup and render methods, gets the context. This is implemented in TypeScript. If you're not familiar, that's okay. I'm not using very complicated things. You can also look at the JavaScript after if you're not comfortable with this. So basically, I'm just going to do some standard stuff. So I'm going to create a VBO, bind it, and put buffer data. So this coordinate system is rendered using just simple quads. A couple triangles. So this is always where the large part of the code goes into when you do WebGL. So I have to prepare all the vertices, and I have these colors for the X, Y, Z. So this is kind of the largest part of the code. It's just putting the data in. If you're familiar with WebGL, you know how that is. So the other thing that I have to prepare, obviously, is the render program. I made a small utility. It's just creating the shaders and then compiling them, linking them into a program. So there's the vertex shader, the fragment shader. I made a very simple one. So the colors are stored as attributes, and the positions are another attribute here. And then I just pass in the model view projection matrix. These two, they come from the camera definition. I will show this in the code. And this one is basically where I want to place my render coordinate system, which is basically the mouse position projected first to map coordinates and then projected into render coordinates. And then you have basically the basic projection times view times model times the vertex position. I'll pass the vertex color as a varying and then render it here with the fragment shader. So the actual render function now looks like this. There's a little bit of stuff like if there's no point to render, then don't render anything. I store the screen space position, like XY pixel, and then I convert it to map using the view.toMap function. So now I have a point that's in map space. And then I use render coordinate transform add to get this transformation matrix from my map point. And this transform I can then use to transform like the local space of this coordinate system that I have, like just 0 and 1, and then transform it into render space. I'll use the program, set up the uniforms for the matrices. So this is just view matrix, projection matrix, and this custom transform, like the model transform that I have. bind the buffer, enable the vertex attribute arrays, like set the vertex attribute pointers. I will disable blending and I'll enable depth testing for this one. And then I draw the triangles. So I have 36 here. And at the end, like I mentioned before, it's important to do this. So that's when I say you're kind of on your own. Like if you do something wrong, things won't render after, right? So be sure that you call this, otherwise the context will be in the wrong state and you will, like the earth will not show up or anything like that. So be sure to do this. So this is pretty much like straightforward WebGL, right? There's a couple of things you need to know, like, okay, the render coordinates transform, but we provide this method for you. Afterwards, it's just pure WebGL, pretty straightforward, but you have to know what you're doing. All right, that's for the render coordinate system. Let's look a bit more at camera and lighting. I already touched on camera. The default things are really simple, so you just take the view matrix, take your projection matrix, and then multiply them and transform your coordinate system, your vertex coordinates. So for lighting, I made a small sample here. I can basically hold like the mouse down and place cubes. So these cubes are rendered with external render. So same as before, I just make the VBOs, all this kind of stuff, and then set it up, render it, etc. But obviously, if I render it as like the coordinate system before, then I don't have any lighting. So now I can. Here I change the date time of the Earth, and then, okay, so these things are not actually properly lit as the way that we would do it with other objects. So let's have a look at how we can enable lighting. So here, if I enable this, now I pass the information and do the shading on in the fragment shader, or in this case actually the vertex shader, to get proper lighting. So you can see as the sun moves, I properly lit the cubes from the right location. So let's have a look. So here on the left you can see kind of a small snippet of what this is. Basically you need to have the normals, you need to have like incorporate the directional lighting, and this is just doing a simple Phong shading, then multiplying that weight basically by the color, like the diffuse color from the sun that we compute, and an ambient color. So these colors, they are not just white. We do compute, like when the sun is going down, we compute kind of a little bit or some effect of atmospheric scattering where the light changes. So in the evening, we have a bit redder, more red light. So this is incorporated. So if you want this same effect, you can see it on buildings, for example. If you have seen this in the scene viewer, we do this. Then you will have to incorporate these same colors. So let's have a look at the code. So all the setup is the same, right? I don't know, I don't have to show, I guess, the other parts where, okay, you just create the vertex buffers and add the cubes and all this kind of stuff. You can look at this later if you want to. So let's look at, so the camera is actually just the same. So we already seen this, view matrix, projection matrix, you're fine. Now for the sunlight, we expose basically three things. We have the sunlight diffuse, so the sunlight comes from the context. So it's just context.sunlight, right? The sunlight definition. Diffuse color, ambient color, and direction, so a 3-vector. What we do, we separate out the color and the intensity. This is something that ThreeJS also does, so we did it like this so it's easier to map it. So here, in this example, I don't use ThreeJS, I just want to pre-multiply the intensities by the colors, so I have a little function that does this, and then gives me the pre-multiplied intensity color. I have this uniform to enable or disable the lighting, so I can do this in the UI, and then I just render. Same thing as before. The only thing that I'm adding is the normal matrix to transform the normals so that I can do proper lighting. This is all very standard, like diffuse lighting. So let's look briefly at the shader. It gained a couple of uniforms for the lighting. So we have the normal matrix, ambient color, lighting direction, directional color. And then what we're going to do is the same thing. So project it. We're going to multiply the normal that we stored also in the vertex attribute by the normal matrix, normalize it, and then use it here to do the lighting equation. Right? This is what I showed in the snippet. Output the light color, and that's it. And then the fragment shader is just going to take that color and then I mix it here so that I can actually efficiently disable and enable without doing conditionals. You can also do it differently, but basically it just says, okay, if I have that enable lighting on, I will take this color, and otherwise it will just be completely white. So that's integrating lighting. You can do other kinds of lighting if you want to do more thematic lighting or maybe different kind of light sources. Obviously you can do this, right? So this is just the basic lighting that we do ourselves in our objects. If you want to match it, then you can do it like this. So dealing with precision issues. So this is something that we don't really want you to think about, but that you will just have to think about. It's something that we cannot just make it go away for you. And if you have been doing WebGL, then you know about this problem. If you have large render coordinate systems, then you're gonna have precision issues. So the problem here is that because we're on the globe and the origin of our coordinate system is really at the center, if you're on the surface somewhere like on meter scale, you're gonna have very large coordinates with very small objects. So here I'm gonna show what the problem is. So I have the same, I add cubes here. So let's add a few cubes. So you can see I added one here, but it's not even visible. There's so much Z problems that I cannot even see it. And as I move around, I get all this flickering. So the solution for this is to put the origin of your render system somewhere else than in the center of the Earth. So I'll show that how that works. But if I do that and I add some more cubes, now they are perfectly rendered without any precision issues. And the basic idea is that you just put, instead of the origin at the center of the Earth, you put the origin here and then set up the transformation so that you use that origin instead. So there's two steps to this. The first is that when you add an object, you'll have to make sure that you basically subtract this origin from where the object should be. So the idea is that you just transform it into that origin space, right? So here's the flag. Okay, if you use a local origin, here I hard-coded it, it's somewhere in this area. It doesn't have to be very precise. I mean, there is enough precision. So you can have relatively large areas around there and you're fine. But sometimes it depends. Maybe you need multiple of these. If you have small objects, but on a very large range, you might need that. This is a bit up to you how to design that. So we get the coordinate transform, we just subtract the origin from the translation part of this matrix, right? And that's the model matrix that we're gonna use. So we store it here in the object. This is the same as in this one, this example before. So that's the first step. Now these are properly with respect to this origin that I chose to be here. So the other thing that you now have to do is to do the transformation on the view matrix to also be in this origin. Because the one that we give you is going to be origin 0, 0, 0 at the center of the Earth. So it's relatively straightforward. We use GL matrix. If you have been doing WebGL, I think you know about this library. It's very useful. You can do it all by hand, but don't do it because you'll make mistakes. I mean, it's really convenient to use GL matrix. It's still kind of not very nice to do all the computations, but I think it's the best thing currently available. So what you do here is you just take the origin, we stored it in this object. That's the origin that we used before, this hard-coded one. And then we're going to translate the view matrix simply by this origin. And that's it. So now we have the view matrix also at the same origin. And if you would look at the transformation matrices, now they are all very small numbers, or in very small, not very small numbers, but in the same I say range, or it's basically on the same scale as what I want to see the objects on, meter scale, for example. It's not going to be, hundreds of thousands of meters multiplied by hundreds of thousands of meters, stuff like that. And if you do it like this, after in the shader, you don't have to do anything special. You just have to do the transformations exactly the same way. I didn't touch this, but if you do things want to do things like eye space, lighting, for example, then you sometimes need to care about which origin you choose to compute the right directions and things like that. So just be aware of changing these origins of the transformation. Okay, so that's about the basics. That's I just showed rendering cubes. If you want to render already rendering cylinders, you have to do all the computation, do all the vertices. this is kind of hard, right? It's like nobody wants to do this by hand. So I want to talk about integration with three.js. I mean, if you have been doing this, you probably know about this library. I think it's the most popular one right now. And the nice thing is you can use higher level abstraction. So you have a scene graph, you can just put objects in there. They have a lot of primitives, geometries, things like that. It's very popular. There's a lot of examples, a lot of documentation. So if you're gonna do external rendering, I would recommend using three.js unless you run into certain issues like performance, for example. So I just wanted to show some examples. Okay, I guess it went offline. This is, I like this example, but I guess it's not there anymore. I just found this on the three.js website. This one is kind of interesting. It's like a globe, but has like a oil, I don't know, drilling stations or something on it. I hope it loads. Let's wait a little bit. Yes, but I have a cable. Yeah, but okay. I mean, I have other stuff to show, so it's not so important. Let me try to show this one. This one is interesting. I showed this last year, like the integration of this kind of thing, where, for example, they have a shader that does kind of ocean simulation. So, and it's a lot of fun. Like they provide all these examples, and you can just play with the parameters and all this kind of stuff. And this is cool because you can take that code and integrate it, right? So there's a lot of things on there, very, very useful, and people do great things with that. So let's have a look at how we spend a little bit of effort to make this easier for you to integrate this with our rendering. So let's have a look at what this looks like. So here I have it's still a simple example. I basically add cubes into the world. I think I also made them kind of scale, so based on your current scale. And you can see that the lighting is integrated, and the things are rendered at the right location. This is using only three.js now, no more pure WebGL. I put on the left here like the most important things that you would need to know, which is the render coordinate transformation, how to put, like, you get the rendered coordinate transformation in the 4x4 matrix, and then you have to somehow put this into three.js. The other thing is how to transform our camera definition into their camera definition. So let's have a look at how that looks like. So let's start with the setup first. So I'm assuming you know a bit like three.js, how like the stuff works, like what kind of things they have, like the render, the scene graph, stuff like that. So I won't go into this. But there's a couple of things that you need to know to properly integrate this with our engine. So first you can create the WebGL renderer of three.js. You provide the GL context that we have, that we give you in this context. Set pre-multiplied alpha to false because we don't do that right now. There's a couple of things you have to turn off because they're gonna try and clear the depth buffer, the stencil buffer, the color buffer, just throwing away all the stuff that we just rendered. So be sure to turn that off. The last kind of tricky bit is that they also sometimes switch render targets, like the FBO, the frame buffer. So they're gonna render to some off screen and then switch back to the main color buffer. But actually for us, this is another FBO. And there's no real clean way. I think we're gonna try to somehow upstream this hack into three.js to properly support it. But for now, what we do is we take the renderer and just override this method that they have, set render target. And if they are going to call this function with null, which means bind the main like color buffer, we're actually gonna secretly bind our target. And then basically it's gonna render again to our FBO. Right? So this is important to know. You can also see this in the sample. You have to do this, otherwise it doesn't work. We create the basic perspective camera, three.js camera. We'll see, we provided here the arguments, but actually we're just gonna update afterwards the matrices directly into that camera. And we also initialize a scene and basically add two lights definitions that they have that match our lighting situation. So one ambient light, it's gonna be the ambient color of the sunlight that we have, and one directional light is gonna be our sunlight. All right, let's see. So that's about the setup. let's see about the rendering. So let's first look at the camera. The camera, basically what we're going to do is make sure we set the viewport. So when you resize the window, make sure that the viewport that is used in ThreeJS is the same as the one that we use. And we're going to do something simple. We'll just set the position of the camera to the eye, the up vector to our up, and then we're going to use lookAt to actually look at the center of our camera. So this is going to provide the full camera definition in terms of the view matrix. And then the other thing, we're just going to directly set the projection matrix of their camera to the one that we have. This will define the camera correctly so that if you render in ThreeJS, it's going to render in the right coordinate system. For the lighting, it's also pretty straightforward. We try to keep the same definition, so it's easy to map it. You have the directional light. We just set the sunlight direction. Intensity goes to diffuse color intensity, and the color is going to be a ThreeJS diffuse color that we just create like this. Same for the ambient light. We just have the ambient intensity and the ambient color. So we create these two lights, and now you'll have proper lighting the same way as we do. Now if we look at the rendering, so that sets up the state for the camera and the lights. Now we have to render. First, yeah, I'll have to call, so they have the same problems as we do, obviously. If we change the state and we don't tell ThreeJS about it, it's also going to go wrong. So we have to reset their state as well. So it's going to reset the cache that they have of the whole WebGL state, and then so to make sure that they don't make assumptions of the state that are not true. Then we're going to render. This is just ThreeJS, right? You'd say render this scene with this camera, and that's it. And then we're going to reset our WebGL state. So this is always important to remember. Reset the state, render, reset the state. The other thing that I will show this after actually. That's the request render. I will get to that. So just to quickly go, okay, how do we add these cubes? So basically just make a box buffer geometry, add the mesh Phong material to get shading, add the mesh in, apply the transformation. This is just taking a map point, doing the render coordinate transform at, and putting that into the mesh, into the ThreeJS mesh. Let's have a look here. So basically get the coordinate transformation, and then we use this decompose method to directly decompose this ThreeJS matrix into position, quaternion, and scale of the ThreeJS object. This is kind of the simplest way to transfer the transformation that they need to do. All right, so that's for rendering. This is the smallest basic setup for ThreeJS. These are the things that you need to do to get this going. Oh, one thing. Let me show you one thing. So you saw at some point there's request render, not this one, but this one. So each time you make modifications and you need to render, you have to call this method. We will not render anything unless we know that we need to, unless there was a change, and these changes we cannot observe. We do this so that the laptops don't go crazy. We don't render every single frame. If there's nothing new to render, we are not going to render. So if something doesn't show up, just make sure that you didn't forget to do this request render, so it's actually going to render a new frame. Okay, so let's look at something a little bit more fun. So the thing that I wanted to show is, because that's something that we don't really do ourselves right now, is animations. So all the data that we'll show you here is static. This is going to probably change in the future, but we don't really know exactly when. If you want to do animations, this is one way to do it. So I made another example. Here, if I click in the scene, it's going to add an object that is loaded from a Collada file by using ThreeJS Collada loader, and it has an animation inside like a keyframe animation inside Collada. And then I'm just going to go over that, animate the keyframes, and then add the objects into the scene, render them. So I want to quickly show what this looks like. So I'm going to refresh so it doesn't doesn't render all the time. So basically what I did is, I'm not going to do the whole thing here, but who knows Blender? Is that familiar? Yeah. So I use Blender for this. It's very basic. You just do keyframe animation. I made a small cube here, and if you go through it, I just made it squash down first, and then go back up, and then kind of squash back in, do a simple rotation, and then go back down. So if I play this, this looks a bit like this, right? So this is what you saw in the animation. And then you can export this to Collada here. And then you can use the three.js Collada loader to load this in and do the animation. Let's have a look at the code for this. Oh, okay. Okay, so the basic setup is always the same, right? We already seen that, the three.js thing. Let's have a look at what we have to do to add this Collada model. So I use the Collada loader. This is not part of core three.js. You have to download these modules, but you can do that. Basically, just load this model, and then we're going to pull out certain things and set up the animation. So we get the basic object from the Collada scene. We just have the single object, actually, in this case. I'm going to apply the transformation as we do usually. So this is going to be at a certain map point. You've seen that before. I'm going to kind of scale it to the view scale so that independent of the scale, I can still see the cube like jumping up and down. You saw that like depending on what scale I am at. That's just for convenience. That doesn't really serve any like functional purpose otherwise. I'm going to update the matrix of the three.js object to make sure that it's applied, and then add it into the three.js scene. For the animation, so this, I didn't really know how this worked, so I just looked at the samples on three.js, and this is how they do it. So basically, create a new keyframe animation. There's some properties, like you can scale it up and down in terms of time. You can make it loop or not. This didn't actually work for me, so I don't know exactly what that is, but you can set it to false, I guess, to make it work. I just did the looping myself. Start to play it, and then I will store this keyframe animation. Again, I made changes. I do request render. Now, during the render, I'm going to update the animation. It's just going to walk through this list of keyframe animations. This is the custom looping. So if it's just past the current, like the end frame, I'm just going to stop it and restart it. I mean, if you're more familiar with this, I would be happy to get feedback on how to do this more properly. I'm not sure if this is the right way, but it works. And then update the animation, and you give it a time step, and then basically it animates. So because I do animation, now every time I render, if there's any animations ongoing, I will have to call request render. If I don't do this, let's try. So I comment this out. Let's reload it. So now you can see it was kind of animating, rendering, but it's not anymore. If I start to move here, it actually animates again. This is because we only render when we have to, right? So be sure to call this request render method if you do this. Okay, so that's for animations. Another fun thing, so I'm just going to show, I just came up with a bunch of things to show. I don't know, some of them might be useful, some of them maybe not, but it's just to give you an idea of the possibilities, really. This is also something I kind of showed last year, but in a different way. So I'm just going to wait a bit for it to load. So this is integrating video textures into your scene. So this is going to basically, any kind of video that is supported by the HTML5 video element, integrated into the scene using three.js. So this is also not really loading very well. Let me just quickly check. I can probably do it without there's supposed to be like a couple of buildings here. Let me try to do it without that, or let me try to refresh first. I'm gonna go a bit in the code and then try to let it load. So if you've done this before, it's not actually that hard to do the video texture kind of thing, because three.js can support this out of the box. So basically what you're gonna do is create a video element. This is like standard HTML5 video element, set the video URL, make sure it doesn't display because we don't really want to show it. We just want to take out the texture and show it in the scene. So I'm not gonna autoplay it, I'm gonna play it on click. I will show how this works. And basically, I still have to add it, I think, to the DOM. I'm not 100% sure if that's true. You can try not doing that. I'm going to store it so I can reuse it later. And then I'm just going to make a texture, a three.js texture, and give this as a source. If you know WebGL, this is supported. Like, you can just create a texture from a video source. It won't automatically play the video in the texture. Like, it won't upload it each frame. But it will take the current frame of where the video is at. So you'll have to do this each time. So now I have the video texture. Let's see how we have to render it. So there's update video. Basically, it's very simple. It's just going to say, if the video is not paused, like I can pause and play it, then I'm just going to tell, OK, you need to update. Every frame, you need to update. And three.js is going to say, OK, I need to update this texture from the source. It's going to take the video source and update the texture. Let's see. OK, I have a couple of buildings. So I hope they stay around. So let's try this. So I made it so I can kind of control click into the scene and drag a kind of billboard on top of a building. So let's see how this works. I'm sorry, I tried to use the mouse, but somehow it doesn't work. So I have to use my trackpad. OK, so I drew basically this billboard, and it's going to play my video. So this is pretty simple, right? You just do this in three.js. It's going to update the texture and run this like Esri brand on top of this building. It's a nice billboard, really. You would also have the sound. I guess you cannot hear it. Can you? No. So I can play this. I can pause it. I can reset it. So there's something's going on here, right? So I did it so that I can actually drag it, and it's kind of on top of on the face of the wall. This is not very hard to do. The way this works is I just take the coordinates in render space. So each time I do a hit test, take the map point, transform into render space, and then I can compute like the angle, the rotation angle that I need to use from that. Let's say you basically have the normal of that plane then, and then you rotate this billboard on top of the building. Obviously, only works for rectangular surfaces, but you could do this in other ways also. The other thing is, if I have it here, like if I click on it, how do I know that I actually hit this object? So to know that, I'm going to show you another example snippet code here. Let me try to find it. So on click, I'm going to call this method intersect screen mesh and give it the X and Y pixel positions. This is also pure three.js, but you have to do a little bit of transformation to get into the right pixel screen space. So basically, this is just going to be X from -1 to 1, and this is going to be Y from -1 to 1. You just have to flip the Y coordinate because the Y that you get is the same as the normal HTML event system, but we need the origin really to be at the left bottom, right? Make a little vector, make a raycaster, and then we're gonna call the raycaster. We kind of update the transformation is also dependent on the camera for the raycasting, so we have to add this. This is the three.js camera that we are always updating, so it's good to go. And then gonna call intersect object. I give it the screen mesh. I'm just gonna check if it intersected it. So this is basic three.js intersection raycasting. And basically, as soon as you know, OK, I hit it, then I'm gonna play the video. You can do other stuff with this. This is just to show you how to set up this, properly do the raycaster. So you can use this for other things as well. So I still have a little bit of time left, but not too much. But I'm gonna skip a little bit over this. You can look at this yourself, this SDK sample with the windmills, how this works. There's quite a lot of all of the setup, loading the models, all this kind of things. So it's pretty involved. If you want to know some more details, see a larger example, you can look at that. I want to talk a bit about this visualization that was shown also before. So this is not, this kind of visualization probably, right? It's not a novel thing. There's Windy TV has done this. There's this Null Earth School simulations. They're really, really cool. They're really, really well done. I like them so much that I wanted to try to do this with the external render. I was not actually sure it was going to work out. So I just tried to hack it together. I will go a little bit over how this works. So the important thing with WebGL really and JavaScript is try to push as much as possible to the GPU, right? This is already true for OpenGL or DirectX, but it's even more so true for WebGL because you don't want to spend any kind of time in JavaScript on doing any kind of processing. Like if you want to do particle simulation on the CPU, you'll be very, very limited to the number of particles that you can actually support. So for this demo, I wanted to really have a large number of particles, so I want to do everything on the GPU. And it's just going to take me 2 draw calls in total to do the whole simulation. Everything runs on the GPU. So the idea behind this is really that, and I'm going to go a little bit quick over this, but we can talk about it after if you're interested. There's basically one texture represents a velocity field. This texture is covering the whole world extent, basically, like full globe extent. And then each cell just gives me x, y velocity vector. These are RG channels of the texture. I got this data by processing in ArcMap, like from NOAA, got the data, process in ArcMap, publish it as a raster server, and then just get the image from there. You can use any other kind of image as a velocity field. You don't need to use image server if you don't want to, but it's a kind of convenient way. The second thing that's kind of hard to do is the whole reprojection. So I want to simulate these things in map space, but then I need to render them in render space. So how can you do that? If you want to convert like manually from Web Mercator to render coordinates, it's kind of involved. So you don't want to really do this on the GPU. Maybe actually you can, I don't know, I didn't try it. But a simple way to do it is just to pre-compute this. So what I did is I just call this the reprojection texture. Again, index this with, let's say, with a map point, and what I get back out is the render coordinate. And I pre-compute this first one time on the CPU. So it's a little bit tricky because actually we cannot use floating point textures in WebGL 1 if you want to also do linear interpolation. So basically we also do this in our engine where we pack, maybe you know this, like you can pack a floating point number into an RGBA channel, into 4 RGBA channels. Then we need X, Y, Z to get like the full transformation out, right, of the coordinate system. So we just have 3 textures like that. One for X, one for Y, one for Z. And you're gonna just sample those textures with the position of the particle and get out the particle position in 3D render space. Last texture is the particle state texture. Each pixel in this texture is gonna represent the particle. It has an X and Y position. This is actually a floating point texture because we don't need any interpolation there. We just want to sample them. So we have X, Y position. There's a kind of life cycle parameter or state that is stored in there. And there's a stream position. And then we have like a texture of n by n particles. I'm going to skip over this. I briefly discussed this. So I took the data from Nomads. It's publicly available, processed in ArcMap, and published as an image server. You can do this in different ways if you want to try and reuse this kind of simulation. As long as you have a texture that represents a velocity field, then you're fine. So in the update step, I'm going to manage the lifetime. So this is running on the shader now. Manage the lifetime of the particles, so they kind of appear in a random location, then follow the velocity field, and then kind of disappear, reset to another location. So you have to manage this. Sample the velocity in the velocity texture of the particle and update the position just based on like simple Euler integration. So you're just gonna do like, okay, put velocity times time step, and then just update the position of the particle in the texture. So this is using an off-screen buffer, right? You do this kind of flip-flopping, so you have like texture in, particle state, and then render to texture out, particle state, and then you swap them like that. If I'm going a bit fast, it's because I'm running out of time, so I'm sorry. Render step, okay, so we take the particle, so it has X, Y in map position, use the reprojection textures to reproject into 3D space, and then color it based on this velocity texture. You can use different kind of coloring. I guess you can go wild on the kind of customization on this. And then in the end, you get something like this. So here, there's actually 1 million particles, and it's running at 60 FPS. It's not really stressing out my machine so much. I didn't try to push this, so I don't know what the limitations are. But you can see that the visualization is pretty nice. So each particle is here represented as a single point. I draw the lines between a certain number of particles that all follow the same path, and then they kind of Like the way this works is all the particles start in the same position, and then the first starts to travel, and then the second and the third, and they kind of like stretch out from there, and then they travel as a line, and then they kind of collapse again, and then they're all reset to another location. I cannot go into all the detail here. I maybe have like 2 minutes to go into the code, but it's kind of large, so I have to apologize for that. If you want to look at the shaders, maybe it's the most interesting. Most of the other stuff is just kind of bookkeeping and making sure that you pre-compute the right reprojection and things like that. So that's the update shader. Basically, because the particle says every pixel, right? So the vertex shader doesn't really do anything, but the fragment shader is run for every particle. There's a bunch of stuff, but this is really the meat of it. So this is life cycle management. We store negative time to say like, okay, this is how much time it takes until you get alive, until you're actually rendered. And then we store positive time to say, okay, this is how long you should be alive. These are just tricks to try. I mean, we only have 4 floating point numbers really per particle. So we have to kind of deal with that state. You could use multiple textures, I guess. I don't know if it will work out in terms of performance. Then we check if the particle actually should die out, and then reset position. We just do some randomization, and then reposition the particle, create some kind of random time of life. So I'll try to document this a bit out more if I publish it online, so it's a bit easier to understand, but you can also just ask me feedback on that. And then this is the actual update of the particle. So like I said, it's really just doing like particle XY update by the velocity here times the time step, times some scale that I just hard-coded to, like the velocity is a meter per second in this data. Obviously, I don't want to show it at that rate depending on the scale what you're looking at, so I just put this number in just for this demo. Rendering, it's going to do basically sample the position, and let me see here. So this is like, remember that this negative time that I store here? If it's basically should not be rendered, I just push it outside of the clip space so it doesn't render. If it should render, I use these reprojection textures, get the XYZ positions out, and then I'm just gonna project like normal. So it's just a point in render space, right? There's some tricks, like there's some Z fighting, you know, all the stuff that you run into when you do WebGL. So I push out like a bit into the screen so that you don't Z fight so much with the terrain. There's a bunch of that stuff. I think that I'm gonna stop here and just give you guys some time to ask questions if you have any. Are there any questions? I think this is my last slide. Oh wait, let me summarize. So the important thing is you have to really understand like what the cost is for you as a developer to use this interface, right? So one is you call Esri, they're going to say we don't support it. Like you won't have technical support for this. You can probably send emails and sometimes, I mean, this trickles down to us and we can help you out, but it's not going to be on the level of official support. And it's really up to you, right? You have to write the code. We're not going to write it for you. It's going to cost you time as a developer. So you have to be comfortable with this. Look at the samples, use three.js, really, like, that's the greatest source. So you can use all their samples, all the documentation. There's a large community, people asking questions, things getting solved, Stack Exchange, all this kind of stuff. And lastly, I make really, really cool visualizations. We are always really, really interested in seeing what you guys can do with this kind of stuff and making interactive applications. So that's the end of my presentation. Are there any questions? No questions? Otherwise, just come to me if you have a question like more detailed. But thank you for listening.